to record.
Can you see my screen?
Right. Looks good. We see your slides and then also your kind of slide preview on the left-hand side. So I think that looks okay.
I'll go ahead and so good morning, everyone. My name is Cheptonui, and I am a PhD student at Colorado State University. And I'm currently the student on the ADED project, which I'm sure most of you know about. And today I'm going to be presenting on the performance of the continuous monitoring solutions that we tested on the third round of testing using the single blind control testing protocol. And so before we dive into the continuous monitoring solutions, I'd like to discuss about the ELDA programs, which is sort of the basis of the continuous monitoring solutions and why we are performing the testing. So with the leak detection and repair programs, an operator uses systems such as the OGI camera or any instruments on the EPA method 21 to detect an emission. And after a couple of days, the operator may schedule a repair. And once the repair is done, the operator may go ahead and detect or diagnose if the leak is still there or not. And that's how the ELDA program works. Some of the things that ELDA work is there is an optional quantification, and it also requires a trained surveyor. Moving on to the next generation solutions, which includes the continuous monitoring solutions. This spans from survey methods such as source vehicle-based or UAV surveys and point sensors and scanning or imaging solutions, which is sort of what we do, the continuous monitoring solutions. So what happens with next generation solutions, if there is an emission source from an equipment in a facility, the emissions are transported downwind, and these next generation solutions rely on emissions being transported by wind downwind, and the solution detects or quantifies the emissions. Some of the advantages of next generation solutions include they offer great autonomy and they may provide data for a continuous period, which is why it could be preferred in place of the ELDA programs. It may offer quick emission detection, and some of these solutions may also offer quantification, that is letting you know how much the source is emitting at. So the figure on the bottom right shows some of the point sensor networks that are installed at a facility and some of the scanning or imaging solutions. These are the solutions that we are testing. And on the next slide, we are looking at the continuous monitoring solutions. So with the ADED program, we are testing the solution as a whole, which consists of a sensor, a natural gas sensor, and the deployment strategy and the analytics. So the sensor will provide the concentration measurements, and the analytics will either infer the presence or absence of an emission at a facility. And as a whole, it consists of a next generation solution for emission detection and quantification. This continuous monitoring solution have some advantages, which could offer, as I said, greater autonomy. It may offer quicker detection at a facility as opposed to the solutions used for the ELDA program. And it also may offer the quantification. Moving on to the ADED project, which is the major topic for today. So with the ADED project, the reason why we have the project is to accelerate the transparent and rigorous scientific validation of leak detection and quantification solutions. So with the ADED project, we do both control testing at our MITEC facility and the field testing at various pilot sites. With the control testing, we use a continuous monitoring protocol and a survey protocol for survey solutions. And the results of both the control testing and the field testing can be used in the ELDA simulation tools such as MEET or MAZE and FIST to determine the efficiency of these solutions. The focus of today's presentation will be on the LDAQ continuous monitoring solutions, and we are going to focus on the control testing, looking at the performance of these solutions and the protocol that we are using. Moving a step further, looking at the control testing protocol. This protocol consists of 4 major activities: the installation part, the maintenance, the operation where we do control releases of natural gas, and the reporting where the solution providers send in their detection reports or their offline reports. So some of the objectives of why we are testing these solutions and using the control testing protocol is we aim at assessing the key performance metrics for each of these solutions and determining whether it can be used in place of the ELDA program solutions. The protocol also ensures that the method we are using is reproducible, that is, it can be used elsewhere, and it's adaptable to field conditions. And we're also testing the solution as a whole. We don't test the specific gas sensor. And the major objective of this presentation is that with the control testing protocol, we are aiming at tracking the performance of continuous solutions over time. That is, solutions that have tested since the first implementation of the protocol and until the third implementation. So figure 1 here shows a view of the continuous monitoring solutions. So with the ADED protocol, we're using pads 4 and 5, and some of the solutions have an option of installing their solutions on or near all the equipment groups that we are testing on, and some solutions may prefer to install their solutions on specific equipment groups. Figure 2 here shows an example of the control releases that we conducted in a specific day. So with the ADED protocol, in a specific experiment, we release between 1 to 5 emission points per experiment. So for example, the first experiment from 4W, pad 4S, and pad 5S has 3 different control releases from 3 different equipment groups. We can release up to 5 different emission points. So once we do control releases of gas, the solution providers have they have to submit detection reports or offline reports. So with the classification process, the control release can either be classified as a true positive or a false positive. For a true positive is whereby the solution provider correctly identifies the source of emission, and with a false negative is whereby the control release, we had control release on site, but the solution provider could not identify the source of emission. As for the detection reports, it can either be classified as a true positive or a false positive. With a false positive is a situation whereby the solution provider identifies a control release, but then we didn't have a control release at site. Another classification that was introduced in the second implementation is the classification of the false positive. So when the solution provider sends in a report and it's correctly paired to a control release, however, when the solution provider sends in another detection report that identifies the same control release, that will be classified as a false positive, but an excess false positive. And some false positive are classified as no control releases, which is cases whereby the solution provider sends in a detection report, but we didn't have a control release on site. So with the classification of control releases, a true positive or a false negative, this chart shows that this specific solution found 67% of all control releases. However, this chart shows that these specific solutions send in 92% of their detection reports as false positive. So it shows that some solutions may have high true positives, but it also could mean that the same solution could be sending in multiple detection reports. That's why we have high false positives. Moving on to the primary metric that we are assessing with the ADED protocol, that is the probability of detection. So by definition, the 90% detection limit means that this is the emission rate at which the solution will detect emissions 90% of the time. So with this figure, it shows a probability of detection curve, which is generated based on true positives and false negatives. We use power function to generate these graphs. This plot also shows the uncertainty range for each of the POD curves, which we generate through bootstrapping, whereby the true positives and false negative data points are resampled multiple times to generate the cloud of faded blue curves. In this specific POD curve, it shows that for 90% of the time, this solution could detect emissions that are 3.2 kilograms of methane an hour. So as I mentioned earlier, this is the third implementation of the protocol. The first implementation was done by Bell et al., which tested a total of 11 solutions. The second implementation was done by Ilonzi et al., which tested a total of 9 solutions. All of the studies since the start of the implementation protocol are conducted approximately 1 year apart between February and April. As for the test conditions in the first and the second implementation, we can see the wind speed and the release duration and the release rate, which is some of the factors that we assess when we are looking at the performance of this solution. Now, moving on to what we tested in the third implementation of the protocol. As I mentioned earlier, the testing was conducted at MITEC between February and April for approximately 12 weeks. So with this round of testing, we had a total of above 700 control releases, with the release duration ranging from 18 minutes to 8 hours. We had windy conditions compared to the previous two protocols, and the release rate within the range of the previously tested solutions. We tested both point sensor networks and scanning or imaging solutions. In this study, we tested a total of 13 continuous monitoring solutions, and comparing it with the second and the third implementation. So relative to the second implementation, four solutions we tested, and relative to the first implementation, 3 solutions we tested, noting that 2 solutions, solution D and F, have consistently tested since the start of the protocol. With the added continuous monitoring testing protocol, we always test for detection, and some solutions may test for quantification, meaning that this solution will send us the source emission rate. Now, moving on to the results of the current testing, we are going to look at first we'll start looking at the primary metric that we are assessing for all the continuous monitoring solutions, which is the probability of detection. So with the POD curves, we can always generate the POD curve as a function of many variables, but in this case, we are presenting the POD curve as a function of the release rate. These plots shows the probability of detection curves for the 4 solutions that we tested relative to the second implementation of the protocol. Generally, with the POD curves, 6 of the 13 solutions that we tested have a 90% detection limit that is within the range of tested control releases between 0.5 and 6.8 kilograms of methane an hour. As for the solutions that we tested relative to the second implementation of the protocol, 3 of the 4 solutions have a 90% detection limit, which was within the range of the controlled releases. As for the changes in the 90% detection limit, as shown in these plots, although the solutions are finding it hard and challenging to achieve a lower 90% detection limit, it's possible to achieve that lower 90%, but it's quite hard. For example, for solution F, there is an improvement in the 90% detection limit and in their POD curve. So for solution F, in the top right plot, in 2023, this solution had a 6.2 kilograms of methane and our 90% detection limit. However, in 2024, that dropped to 0.5 kilograms of methane an hour. As for the other solutions, the 90% detection limit would either drop, but then the uncertainty in the POD curve would remain the same as shown by the overlapping uncertainties in solution D and solution P. As for solution N, there is an increased 90% detection limit and overlapping uncertainty in the POD curve, especially for control releases that are higher, greater than 3 kilograms an hour. Generally, with the changes in the 90% detection limit, we notice a partial improvement in this metric, with 2 solutions having an increased 90% detection limit and 2 solutions having a decreased 90% detection limit. Looking at the classification of detections and control releases for all the 13 solutions, the top plot A, shows the true positives and false positive classification of the detection reports that are sent in by the solution providers. Each of the solutions has at least one vertical bar, with the red representing the true positive rates for each of the solutions and the blue representing the false positive rate for each of the solutions. As for solution D, F, and P, it shows the detection classification for the previous year and for the current implementation. As for the bottom plot B, this shows the classification of the control releases for each of the solutions, the true positives and the false negatives. Again, for solution D, N, and P, it shows the classification for the testing in 2023 and the classification for the current testing. There is different counts of control releases for each of the solutions, because some solutions may send in offline reports, meaning that the control releases that were conducted during the offline period for that solution will not be included in the classification process. Generally, what these 2 plots shows that is that 7 out of 13 solutions had higher true positive rate, greater than 50%. There is a high false negative rate than false positive rate, as shown that all the solutions have a false positive rate that's less than 50%, and 7 of the 13 solutions have a false negative rate less than 50%. This shows that most of these solutions are trying to achieve a balance between the method sensitivity and low false positive and false negative rate. Looking at the localization precision, for the localization precision, we use the count of true positive detections for each of the solutions to localize the source of emissions to either the unit level, the group level, or the facility level. We're also showing a comparison between the performance of solutions that tested in the second implementation relative to the current study. The range of localization precision for all the solutions, all the 13 solutions, was between 22 and 96%. 7 of these solutions have a precision greater than 50% at the unit level. What this plot shows, as highlighted for solution I, solution M, and solution V, is that these are scanning or imaging solutions. When we compare the scanning or imaging solutions to the point sensor networks, we see a higher precision at the unit level compared to the precision at the unit level for the point sensor networks. Generally, for this metric, we have a partial improvement in the precision, whereby 2 of the 4 retested solutions have an increased precision at the unit level. Looking at the quantification accuracy for the solutions that send in their source emission rate, this is not this is an optional metric for solution providers. They can either send in the emission rate or not for solutions that quantify. So how we assess the quantification accuracy for all the solutions is that we do a normalized percentage difference between the metered control release rate and the reported emission rate, and we do a percentage difference. This plot also shows the factors within which the reported emission rate are to the actual emission rate. So the upper plot shows the quantification relative error for the control releases that are less than 1 kilogram of methane an hour, and the bottom plot shows the control releases greater than 1 kilogram of methane an hour. What this plot shows is that for 8 of the solutions, they have greater than or equal to 50% of their emissions that are within a factor of 3. And for all the solutions that we tested relative to the second implementation, they have an increased percent of their single estimates that are within a factor of 3. What this shows is that with the smaller emissions, the ones that are less than 1 kilogram of methane an hour, there is higher relative error compared with control releases that are greater than 1 kilogram of methane an hour. And overall, the uncertainty in quantification estimates reduced when we compare the current study, the performance of the current study, with the second and the first implementation. This is one of the metrics that we look at for the solutions, which is the mean time to detection. This shows the time difference between the start of the control release and the time when the solution provider first sends in a detection report. This plot is shown in decreasing order of the mean detection time, with the ones that have high mean detection time on the left and with the one with the least are on the right. What this shows is that when we compare those solutions that tested in the second implementation with the upper bars, it shows that there is an increased mean time to detection for each of the solutions. However, this might be due to the fact that for some of the solutions, their reporting system might not be fully automated, so they have to manually send in their detection reports. That's why we have this high mean time to detection. We also noted that for all the solutions that tested in the current round of testing, the operation downtime for all the solutions was less than the EPA's less than 10% downtime. We had a couple of limitations with the current testing. So one of the major challenges that we encountered is that for operators, they have to interpret the data, for the solution providers, I mean, they have to interpret the data as opposed to how the protocol requires the solution providers to submit their detection report. Also, as with the mean time to detection, this is a metric that is heavily affected by the solutions reporting their detections, especially for those solutions that do not have an automated reporting system. Also, we note that the results are only representative of the limited test conditions. For instance, for some of the solutions, they may rely on emissions that run for longer periods. However, the maximum release duration that we had for our testing is around 8 hours. For the releases with the ADED control testing protocol, currently the emission rates are steady state, as opposed to in the field whereby the emissions could not be for steady state. We also had a limited emission rate range. So the results that we present are only representative for that range of emission rates, and it cannot be extrapolated to higher or lower emission rates. The installation may also differ from field deployment. So the results of the control testing protocol shows some implications. So the first one being that continuous and rigorous testing is needed for both solutions that are coming up and for the solutions that already exist. This is shown by the solutions that I've tested since the first implementation of the protocol, which have lower 90% detection limit, with that detection limit falling within the range of control releases that we have. We also know that these solutions that are continuously tested having low false positive and false negative rate. These three different metrics show that the solutions are aiming at striking a balance between the method sensitivity, the 90% detection limit, and having lower false positive and false negative rate. We also see that there is still a consistent uncertainty in single emission estimates. In terms of quantification, we see that for smaller emissions, the solutions have higher quantification relative error than for larger emissions, those that are greater than 1 kilograms of methane an hour. There's also another consistent performance with scanning or imaging solutions, which have higher localization precision at the unit level when we compare those to point sensor networks. Generally, we note that solutions may perform well when different metrics are assessed. It's hard to get one specific solution that has all the perfect performance for all the metrics that we are looking at. I would like to thank my co-authors and the funding from the US Department of Energy. Thank you so much for listening in.
Right, terrific. Thanks, Fancy. That was a great talk and really interesting results here.